So this is the plan for the foreseeable future, which is maybe the next, I don't know how long, month or two, probably a month. We're going to talk about rotating black holes. We talked about Schwarzschild. We're going to talk about rotating black holes. We're going to talk about visitor space in more detail. And part of the goal that we have here is to set up and prove the area theorems for hopefully both cases. I should mention that there's some things that I want to do in this course, and I put on the syllabus that I'm not sure exist in the books or the literature, so we'll have to see how much of it we can do. Some of this area theorem stuff applied to the sitter is a little foggy in the literature even, so we'll have to see. Okay, so we'll start with rotating black holes. So that's the topic for today. Let me start with a warm-up problem. Far from a slowly rotating mass, slowly rotating body of mass m and angular momentum j. The claim that the metric is, as r goes large R, that the metric is the Schwarzschild metric. Minus 4j over R sine squared theta d phi dt plus order over R squared j squared terms. So remember the Schwarzschild metric is minus 1 minus 2m over R dt squared plus the R squared over 1 minus 2m over R plus R squared theta squared plus sine squared theta d phi squared. So something to note about this claim, I'm sort of going to prove, we're going to quickly describe how to prove it at least, is that just like how the energy, m, is encoded in the asymptotics of the metric, here it's, you can see it as 1 over r piece of GTT. So if I just tell you the asymptotics of GTT, you can read off the energy of the solution. The same is true for the angular momentum, that it's hiding or encoded in the asymptotics of the metric component GT phi. We're going to have a lot more to say about this later, but for now, I just wanted to note that m in J here are the total energy, angular momentum of everything in the space-time. They're not just the energy in the gravitational field or the angular momentum in the gravitational field. They're really the total. So you take an object that has some energy and you put it in the middle of space-time. Now you go way out towards infinity and measure the metric out there, you can figure out how much energy there was in the minute. All the contribution of everything in the space-time is included. And we should compare Gauss law in electromagnetism, which says that the total charge, Q, is the integral of the flux. Right, so when you have a bunch of charges in a space-time sitting in the middle somewhere, you can figure out how much charge there is by measuring the fields far away. Right? So this is the, if you take your Gauss sphere to be large, this is just depending on the asymptotics of the fields. Whereas on the left-hand side here, we're not talking about the fields, we're talking about the stuff. So like the charge pack. It's exactly the same kind of thing with GR and energy angular momentum. In that the asymptotics of the field are encoding how much stuff you have, in this case measuring for you the energy and angular momentum. So we'll have much more to say about that, but I'm postponing that until the second half of the course. For now, we want to do other things. So I'm not going to derive this claim about the metric, but I'm going to tell you how one would derive this claim about the metric, and you can ask me if you want to see it. I can give you a reference if you want to see it. So this is how you would derive the fact that the asymptotics of the metric around the rotating body look like this. So I'm going to suppose we had a slowly rotating sphere. By slowly, I mean that it's non-relativistic. So it's rotating in such a way that the constituents are non-relativistic. The stress energy tensor of a non-relativistic massive object is just mu of x mu, where mu is the mass density and u is the form velocity. In other words, in the rest frame, it's just, in the rest frame, the stress tensor is just the mass in the 0, 0 component. So 0, 0, 0, 0 components measuring the energy density. I should put it approximately here because I'm using here the fact that this is non-relativistic. So in general, you can go to the rest frame of a particular constituent of some rigid body, but you can't go to the rest frame of all of it if different stuff is moving different ways. And we don't want to go to a rotating frame, so what we want to use is that you can write T mu nu as mu of x times the matrix 1, V1, V2, 3, V1, V2, 3, with everything else order B squared over C squared. And I'm in the basis T, x1, x2, x3. So we just get the spatial free velocity here and the 1, which is the energy density for the rest mass. So V here is omega of x, where x is the angular velocity. Okay, so what are we supposed to do to derive this general fact about the metric of rotating body? Well, since we're just talking about very far away, this is a weak field. This perturbation here is a weak field perturbation, so we can use the general solution of the linearized Einstein equations that we derived last semester. linearized Einstein equations box h bar f beta equals minus 16 pi t f beta. And the general solution is easily written using the Green's function as h bar alpha beta t x vector equals 4 integral t 3 x vector prime t alpha beta of t prime x vector prime ret over x vector minus x vector prime, where we evaluate the stress tensor at the retarded value of the coordinate, which just means that we evaluate it at t prime equals t minus x minus x prime. That is, if we have some object whose world volume rather looks something like this, then we can find the metric perturbation out here by sending back a light cone and integrating the Green's function over this piece of the matter distribution here to find the field that's generated out here. And I'm just not going to do the rest. Okay, so the rest is boring. You can expand out that, you can just directly evaluate this formula for the slowly rotating sphere. We know the stress tensor. We know the totally general formula for the linearized gravitational field. Basically, what you would need to do is expand this out, large distance expansion, and from there you can derive this Holman metric. So I'll just write that. Implies claim. So that was the linearized solution of the vacuum Einstein. We were solving far away, so we were solving in a region where it was vacuum, but we had a source in the middle. For black hole, the name of the game for finding the metric of a rotating black hole is to look for exact vacuum solutions of the Einstein equation. So the vacuum Einstein equation. R mu equals 0. And we want to find exact solutions of that equation, which are asymptotic to the thing that I accidentally just wrote down that I had written in the corner so that I would say that. Okay, so that's hard. This is actually, I think, much harder than Schwarzschild. I can't remember if I mentioned this fact last time. So Schwarzschild wrote down a solution, what, like 1916 or something? And the Kerr solution, which is the exact solution of a rotating black hole, was in 63. Okay, so it was a long time before anyone realized that it was even possible to write down a metric for a rotating black hole. But that's what we're going to talk about, is an exact solution with these asymptotics. Let me start by writing a metric. to define various things after I write this down. Minus delta over rho squared dt minus a sine squared theta d5 squared plus rho squared over delta dr squared plus rho squared theta squared plus 1 over rho squared sine squared theta a dt minus r squared plus a squared d5 all squared where delta is r squared plus a squared minus 2mr and rho squared is r squared plus a squared rho squared theta. So these are called Euler-Lindquist coordinates. There's a trick for deriving this, but we're not going to do it. It's just hard. So this was a major feat to be able to find this exact solution against that equation. What else do I want to say about that? Unlike the case with Schwarzschild, so in Schwarzschild, if you get symmetry, so in Schwarzschild, you say, I want a vacuum solution that's spherically symmetric. It's very easy to write down the most general spherically symmetric ansatz, and relatively easy to go from there to proving that the only possible answer is the Schwarzschild metric. Kerr is not like that. So we can't write down general ansatz for a metric with the right symmetries, and we can't just plug into the Einstein equation. We have to do something more clever. So far away, and when we set theta as pi over 2, make things a little easier. This thing, delta over rho squared, goes like 1 minus 2m over r, which is like the GTT of the Schwarzschild metric. So this is giving the Schwarzschild-like GTT here. And from that, you can read off that the energy of this solution is indeed m, the mass. So m could have just, did I write it here? There it is. Right, so just because I call it m didn't mean it was the mass. To check that it's the mass, you have to expand the metric near infinity. One way to think about it is that you could put a test particle very far from that mass, and it would obey Newtonian gravity. So that's good enough to determine the energy in the middle. And similarly, you can look at the asymptotics of GT phi in this metric. So it's a little messy, but it's easy to do. And what you'll find is that the angular momentum, then you compare to the thing that I erased. So you can just look at GT phi asymptotically, compare to the thing that I erased, and you'll find that the angular momentum is J equal to A M. So the two parameters here are the mass and angular momentum. But it's usually easier to parameterize that by the mass and A, little a, which is the ratio of angular momentum to mass. For now, I'm going to restrict A to run from minus m to m, and we'll come back to why I'm doing that and see in a minute why case is special. Well, I didn't have to restrict just yet. First, let me look at the symmetries. So there are two obvious isometries in this space-time. There are two coordinates that don't show up in the metric, t and phi. So t goes to t plus constant, and phi goes to phi plus constant. If we write those as killing vectors, that is, we think of these coordinate transformations as x goes to x minus c, then the two killing vectors are ct equals ddt, and c phi equals d phi. In fact, this is it. So these are all the symmetries of the Kerr solution. There are no others. The isometry group is r times u1. In general, you can't figure out the symmetries just by looking at which coordinates it's independent of, but in this case, it gets you all. There's a curvature singularity. Hey, that worked pretty well. There's a curvature singularity. So the way to find a curvature, the way to really, you can kind of guess based on what we did for Schwarzschild, but if you really want to be careful about it, you need to calculate a scalar. You need to calculate a scalar curvature quantity and check that it blows up to look for singularities in the metric. Oh, I forgot to mention, I must have missed a page in my introduction. I forgot to mention the most important thing about my introduction to this course, which is you have to use Mathematica in this course. Okay, so I guess you weren't supposed to first semester, but now that you have made it through a semester of general relativity, don't ever calculate a Riemann tensor again. You have to. So it's just terrible to do this stuff by hand, and we wouldn't wish it upon anyone except for a first semester GR student. I think the problem sets will be way too hard if you don't use Mathematica. And beyond that, it's essential in research, so think of learning how to do GR Mathematica as part of the goal of this course. You should learn how to do GR Mathematica. Let me write on the, this is on the syllabus, but there are at least two Mathematica packages that I know of. One is mine, which is called Grader 2. And there's another one called, I think it's called GR Tensor 2 or something like that. And I guess I'm sure there are others. I don't know. What do other people use? What do people use these days?
Maple sometimes.
Maple, is there a package to do GR?
Tensor, GR Tensor, something like that.
Okay. What?
Exact.
Oh, exact. Oh, yeah. I don't even know how to use that one. That's for symbolic manipulation, I guess. I was thinking more of computational.
Yeah, you can do coordinates in the next side, but it's totally terrible.
Yeah, so there's a package called exact. you need a PhD in computer science to install it. But if you manage to install it, it's like as smart as a graduate student. So exact can do things analytically, like I don't know, vary the curvature tensors, or find the equations of motion, or stuff like that. These other packages are for working components, like you hand it a metric and it spits out the matrix of the curvature tensors. So as far as learning how to do things in Mathematica, come talk to me. I'll post some of the solutions to some of the problems done in Mathematica, and you can read those to see how I did it. Talk to the other students. If you're using Maple, do other people use Maple?
I don't use it, but I know some people.
Oh, some people do. Okay, if you're choosing now, I don't know, what does SolScoop do? But that's for numerical GR. That's a whole different beast. I mean, I meant just like if you wanted to know the Riemann tensor of this metric, that's the kind of problem I'm talking about. So you don't want to use C++ for that. I would say if you're just getting started in doing this and you're not already settled into your ways, then you should definitely use Mathematica. And I'm not sure what the optimal package is, but this is the one that I'll use for writing the solutions. Are there others? Do people know of others? Anyway, so you take your Kerr metric here, you plug it into your favorite Mathematica package, and you can calculate the curvature singularities. So, for example, you can check that this thing blows up at rho squared equals 0. Well, I should say that when you're looking for singularities, the first thing you do is just ask where the metric and the metric and/or its inverse have singularities. If the metric is smooth, then certainly everything's going to be fine. So you just look for where the metric and its inverse have singularities. In this case, those turn out to be at rho squared equals 0 and delta equals 0. Now, that's just enough to determine that there's a singularity in the metric, which could be a coordinate singularity or a curvature singularity. So once you've found those, then you go calculating the curvatures. The rho squared equals 0, 1 ends up being a true curvature singularity. This is a property of the manifold. The other one, as you would guess, is the horizon, actually plural, horizons. So there are horizons at delta equals 0, plural because that's a quadratic equation, unlike in the Schwarzschild metric where there was just the horizon. So we have two horizons. The solutions of delta equals 0 are r equal to r plus minus, defined to be m plus or minus the square root of m squared minus a squared. R plus is called the outer horizon because if you start outside the black hole and you decrease r, it's the one you'll see first, and r minus is the inner horizon. can we discuss uniqueness for a few minutes here? So, why do we care about the question of uniqueness? You know, what we really care about, say, astrophysically, is the metric outside of a star or maybe a collapsed star, or whatever happens to be out there. And in the Schwarzschild case, we had a good reason for talking about the Schwarzschild metric. It was the unique spherically symmetric vacuum solution. So outside of a spherically symmetric matter distribution, like a star, regardless of whether it's a black hole or not, the metric was Schwarzschild. So clearly we should study, clearly there's no doubt about it, we should study the Schwarzschild solution. So there was this theorem called the Birkhoff theorem, which says that Schwarzschild is the unique spherically symmetric vacuum solution. It's certainly not the case that the Kerr solution is the unique metric outside of a rotating body. That is certainly wrong. I mean, you can have, you know, when we calculated the leading term of the metric around the rotating body, that was just the leading term, and we could have kept more multipoles, and all of those, the higher order multipoles are all arbitrary. There's an infinite number of parameters. There is no unique metric outside a rotating body. So why do we care so much? Why should we even bother studying this particular solution here? Well, first of all, because it is one, we can study it. It's an exact solution of Einstein equations. I think that was the initial motivation. But a much stronger motivation came later in what's called the no-error theorems. So the no-error, it's not really one theorem, it's a bunch of theorems proved by a bunch of people, state that Kerr is the unique stationary vacuum solution. And this includes Schwarzschild as a special case. So stationary basically just means that it's reached a steady state. I'll come back and define that carefully in a minute. But physically, the reason this is important is that it means that any rotating system which collapses to a black hole will eventually be Kerr. Okay, so anything that, as long as you wait long enough, everything's a Kerr black hole. So that's why it's not unique in the same sense as Birkhoff, but unique in that if a rotating star collapses, then eventually it is going to be described. Erasing the metric. Eventually, it's going to be described by the Kerr solution. So, if you have collapsing matter, with spherical symmetry, you immediately get the Schwarzschild metric outside of in the vacuum region, outside of that collapsing matter. The assumptions of the Birkhoff theorem did not include assuming that it was static or stationary. It only assumed that it was spherically symmetric. So even while the star is still collapsing, It's not even a black hole yet. You have the Schwarzschild solution right outside. If we draw that Penrose diagram, then you have some star that's like this, making a black hole. Then as long as it's spherically symmetric, and on the outside, as long as it's spherically symmetric, it means that starting here, just at the outside of the matter distribution, this out here is exactly the Schwarzschild. Without spherical symmetry, the no-Kerr theorem implies that it's eventually Kerr. So if you have a gravitational collapse of totally arbitrary matter, no symmetries whatsoever, then who knows anything is happening here. Then at late times, I'm assuming cosmic censorship. Let me come back to that at some future time. I'm assuming that the collapse actually creates black holes. That's not a proved fact, but I'll come back to that. Okay, so assuming you make a black hole, it means that this region out here is to a very good approximation Kerr. So at late times, it always settles into Kerr.
Is no-Kerr theorem only applied to 4-dimensional spacetime or to arbitrary dimensional spacetime?
Yeah, the no-Kerr theorem isn't it depends on all sorts of assumptions. It's 4-dimensional. Certainly the original no-Kerr theorems were for 4-dimensional asymptotically flat space-time and only allowed certain kinds of weakly coupled matter content in the theory. There are certainly cases that are different from that, where no-Kerr theorems did not apply. Black holes can't have hair. But the details of that depends a lot on the details of how many dimensions you're in, what the asymptotics are, and what the matter content. So let me define some of the words that I've been throwing around a little bit undefined. So one of those was stationary. Well, first let me give bad definitions of stationary and static, and then I'll give good definitions. Okay, so the bad ones work for most coordinate systems that people like to use for black holes, but they're bad for reasons you'll see. So stationary just means that the components of the metric are independent of time. So you have translations in the t direction are symmetry. So it's easy to see that that's true for Kerr. General relativity? No? We're doing black holes! No. So a static metric is one that also has GTI equals 0 for I not equal to t. So the difference between static and stationary is basically the angular momentum term. It's the GT. It's the existence in the Kerr metric. It's the existence of the t phi cross terms in the metric that make it stationary as opposed to static. Now you should be grimacing. Maybe Simon's grimacing. You should be grimacing that I'm giving these definitions. They're terrible because they're coordinate dependent. We can't define things based on whether we happen to have picked a good t-coordinate, coordinates are arbitrary, we could relabel points in such a way that there were t's all over the place in that metric, but it wouldn't change the fact that it's a stationary metric. So the coordinate independent definition of stationary is just that there exists a time-like killing vector. That's not obvious from what we've drawn there. It turns out to be true. I mean, we'd have to check whether we found two killing vectors, DDT and DD phi. We have to check whether some combination of them is time-like. It's not obvious, and we'll come back to that. But it's true. Static is there exists a time-like killing vector, and there exists a space-like hypersurface. Orthogonal to that time-like killing vector. We haven't defined hypersurface, probably have some sense of what I mean by that. It's just the statement that you can, well, it's basically the statement that there's a coordinate called t, and that the time-like killing vector is ddt. We'll see better when we talk about the details of Kerr, what's going on, but you could say that it's the requirement that there's a global time coordinate and that surfaces called t, and the surfaces of fixed t are surfaces of fixed t are space-like, and that ddt is a everywhere time-like killing vector. This is easier to explain by the example of Kerr where it won't really work. I can't remember if I mentioned that the axial symmetry, did I say this? That the axial symmetry of Kerr comes out automatically in the uniqueness theorems. It's not put in by hand. So you put in that it's stationary, which gives you one killing vector, ddt, or some combination of ddt, something that's asymptotically like ddt at least. And out of the no-Hare theorems comes the additional killing vector, dd phi. So that's pretty difficult to prove, but it turns out to be true in asymptotically flat space, that just the existence of the one killing vector is enough to get a second one. It's sort of surprising, but you could kind of think of it as if you had any lumpiness in your space-time, like the black hole had, I don't know, why can't you have a black hole with some lumps on it or something? Or maybe some lumps on it. If you had a black hole with lumps on it, then as it rotated, it would emit gravitational waves because of those lumps, and it wouldn't be stationary, and those lumps would decay. One way of thinking of the no-Hare theorems is that basically all of the, so the statement of the no-Hare theorem is that everything is parametrized at late times. All you have is m and j. And one way to think about that is that all of the other excitations of the space-time, all the other multipoles, whatever lumps you could put on the black hole horizon, all of those excitations essentially fall into the black hole. You have you could imagine those are some waves on top of the black hole, but all such waves are damped because they're falling in, and that, I think, intuitively is why there are no Hare theorems. It's because you can't stick stuff, you can't put modes outside a black hole that are just going to sit there, they're going to fall in. It's a little rough, but that's the expression.
The same thing about hard dimensions?
In flat space? There's no, the usual no-hair theorem does not apply to higher dimensions, so for example 5 dimensions. One of the essential steps in the no-hair theorem is arguing that black holes, the topology of the horizon of a black hole is necessarily spherical, S2. And the analogous statement is not true in higher dimensions, so that the topology of the horizon of a 5-dimensional black hole can be complicated. It doesn't have to be S3. So I don't know. So the usual statement does not apply. I'm not sure to what extent there are other statements that do apply.
Question.
Yeah.
The modes that you talked about, can they not bounce back off the black hole using something like a Penrose process or something?
There are modes that can get to infinity, but everything either falls in or radiates off. And so once it settles down at late times, then you're just left with Kerr. One of the striking things about the Kerr metric is frame dragging. This is generally true of rotating objects in GR, that they will frame dragging. So consider an observer, or you don't have to make an observer. Consider a particle on a geodesic x mu of tau with 4 velocity u alpha, which is dx alpha d tau. Now recall that this has conserved quantities associated to it, and for every killing vector of the background spacetime, there's a conserved quantity that's constant along geodesics. This particle's moving on a geodesic. So the conserved quantities in Kerr are just the energy and angular momentum. Actually, sorry, that's false. The obvious conserved quantities for Kerr are just the energy and angular momentum. There turns out to be another one, which I'll talk about. But for now, just the energy E is minus U dot CT, and the angular momentum L, which is U dot C phi. Let's work out the angular momentum. So that's G alpha beta, U alpha, C phi beta. C is the killing vector pointing in the phi direction, so it only has a phi component. So this is just G phi t dt d tau plus G phi phi d phi d tau. And now I'm going to ask the question, what are the properties of zero, of geodesics with zero angular momentum? So these are called zero angular momentum observers. Well, I guess they have to be people or something to be observers. Maybe they're zero angular momentum particles. So zero angular momentum observers are just world lines that have this set to zero. The conserved quantity angular to zero. Just by setting this to zero, we find that they have d phi dt is minus gt phi over g phi phi, which is not zero. So remember the angular momentum piece of the black hole was the gt phi component. And g phi phi component is obviously not. So as a object which does not have angular momentum must rotate around the black hole. Let me draw a dynamical picture for that. So here's a black hole. And you start out way out here at infinity, and you drop something straight. You literally drop it in the sense of you drop it down. Black hole is down there. You just let go. You don't give it any kick in any direction. It starts out going straight. It's not just, if it were Schwarzschild, it would just fall into the black hole like this, and it would hit right there. But for Kerr, so let me put the axis of rotation like this. So it's rotating around the phi direction is this way. If we're on an orbit that starts out just sitting at, we started this object just sitting at rest at infinity. So this is a zero angular momentum geodesic that I'm drawing here, which means that as we approach the black hole, it's going to have non-zero d phi dt. So what is this going to look like? Well, the closer it gets, it's going to start to orbit. It's still going to be falling in, but it's going to be forced to orbit. Sorry, I can't draw. This is supposed to all be happening.
Or it'd be easier if the axis of rotation was outside.
Oh yeah, we can look at it from above. That's good. Okay. Okay, so it's rotating this way. We're looking at it from above. Then you drop something. It's going to spiral out like this. And in fact, I think we'll come to this next time, but in fact, it's going to go around the black hole an infinite number of times before it falls in. So it has to rotate. At the horizon, so if we calculate this rotation minus gt phi over g phi phi at r equals r plus, we can check that that gives a over 2m r plus, which is called omega h, the angular velocity of the horizon. And I think I'm going to skip showing this, but so as this infalling particle gets close to the horizon, it's going to be moving around with this angular velocity. Now here we assume the geodesic equation, right? This was a freely falling particle, but in fact, if you look at the light cone, if you look more generally, suppose this falling observer has a rocket booster, and the only constraint on this infalling particle is that they have to go forward in time. So they're restricted to stay within inside their own light cone, but they're not required to go on a geodesic. In that case, as you might sort of guess, like the closer they get to the black hole, the light cones in the phi direction sort of start to tip, and that you can't, if you're, say you're kind of close to the black hole, you can't counter rotate with as much angular velocity as you would have expected, say in the short shot case. You can co-rotate with extra angular velocity. So your light cones are sort of tipping in the direction of the rotation. If you go all the way onto the horizon, then no matter who you are, it doesn't matter who you are, whether or not you have a rocket booster, the angular light cones actually collapse all the way on top of each other. And so an observer who's sitting at the event horizon of the black hole is actually forced to co-rotate. Will necessarily co-rotate with angular velocity. So the ergosphere, I probably won't have time to do the whole ergosphere in the next 5 minutes, but let me just start talking about the ergosphere. So the ergosphere of a rotating black hole is without a doubt one of the coolest things ever invented, and one of the most important physical phenomena in the sky. So let's look at a static observer, that is an observer whose world line just goes in the t direction, so it's just t of tau. And all zeros. In a coordinate invariant way, we could say that we're talking about people whose fore velocity is proportional to our d dt Killing vector, where gamma here is a proportionality constant, just chosen to normalize u squared equals -1. So this is definitely not a geodesic observer. We already said that, well, we'd have to check if this satisfies the geodesic equation, and it won't. But this is just some observer with a rocket booster who's deciding to sit on these static world lines. Easy. But we better make sure we can't just choose any old fore vector as our fore velocity. People have to go forward in time. So we better check that this killing vector, this fore velocity that we've chosen is forward pointing. And if we calculate the norm of CT using the metric, so G alpha beta, CT alpha beta, then what you'll find is -1 over rho squared delta minus a squared sine squared theta, which changes sign outside the event horizon. So this is equal to 0, and delta is a squared sine squared theta. Which means that if we draw the black hole in Boyer-Lindquist coordinates, so this is the r direction, and we put the horizon at r equals r plus, then you can just solve this equation, delta equals, by the way, you can see that it's outside the horizon because let's look at the equator. On the equator, you can ignore the sign. And remember, the horizon is at delta equals 0. But this surface we're talking about now, where this Killing vector becomes null, is at delta equal to a squared. So this is happening outside the horizon. If we draw a picture of it, it ends up looking like this. And this is called the ergosphere. The dividing surface, this surface delta equals a squared sine theta, sine squared theta, is called the static limit surface, and it's clear why. It's because these static observers that we just decided to talk about, who are moving in the t direction, can't exist inside the ergosphere. This is basically the statement that if you're inside the ergosphere, you must rotate with the black hole. You don't have a choice. You must start to rotate, and you're gonna be forced to. Let me draw one more picture because it's going to be too confusing if I have to draw this next time. So if we look at the, I want to explain basically where ergospheres come from and what's the difference between static and stationary. So if we look in the t direction and we just look at some circle outside the black hole, it's outside the ergosphere, and we could ask, how does that circle evolve to the next circle? So I'm just drawing a circle somewhere around the equator, and then asking how that circle evolves in time. And then we could look at the CT killing vector. So what I'm drawing here, I should make it straight. So I'm drawing the CT killing field. So it's going to kind of do this. That is, the CT killing vector is kind of tipping as if you're well outside the black hole. And when you hit inside the ergosphere, this tipping becomes extreme. Basically, this is why you have an ergosphere. It's because the killing vector ddt starts to tip and becomes a space-like.
One of my goals with this course is to have
I don't know if I made that more than 45 degrees. It's supposed to be very tipped, and that's why this is a stationary space-time as opposed to a static space-time. It's because the t port, or rather the DDT,
with archaeologists studying pretty much anything that humans
maybe I'll finish that next time. So basically, you still have a time-like killing vector, but it's not DDT. The time-like killing vector is some combination of DDT, which is now turned over, and DD5, which sends you back this way. So you still have a time-like killing vector. It's still stationary, but you don't have a global time coordinate t that corresponds to the constant values, to that's orthogonal to that killing vector. Okay, stop there.